Hello everyone. So in today's lecture we are going to study about aberration. Aberration. Alright. So aberration where in optics, where we can see aberration. We can find aberration in our image. That is simply aberration means defect. Aberration means defect or distortion. Distortion. Alright. So we can say aberration in any image. That means we are going to get an defected image. Aberration means simplify we can say that defected image. So if you want the definition for aberration, so aberration can be defined as aberration can be defined as in optics in optics, aberration is a property is a property of optical system of optical system such as such as lenses that causes light that causes light to be spread out over some region over some region of space. So again, in optics, the aberration is a property of optical system, such as optical system like what lenses, telescope, microscope can be anything. All right, lenses that are causes light to be spread out over some region of space rather than rather than focused focused to a point That means if we have an optical system such as this is a convex lens, all right, this is an object or we can say the white light. So object, this is a white light, so this is going to be spread out where in its constant colors. Say this is red and this is blue. All right, if we have, suppose if we have a point object, if we had a point object, that means ideally we say we have a we will have we will have its its point image. All right, this is an ideal case. This is an ideal. If we have a point object, so we will have its point image. But here we can say if this is a white light, so this is spread out into what? Into red color, this, and say this is violet color. So in its constituents color. Alright. So this is aberration. This is aberration. What kind of aberration? This is chromatic aberration. Alright. Because we are dealing with colors. We are dealing with what? We are dealing with colors. So it is a kind of what? Chromatic aberration. So in general we can say aberration aberration aberrations causes the image formed by a lens to be to be blurred or distorted or distorted. All right. So we can see. Let's take an example. Suppose there is a book and there is written something like refraction, or we can say refractive index. Say some word refractive index. So suppose its font is about so small that I can read easily. So for that, just to read this, I need a magnifying glass. Magnifying glass. So when I use this magnifying glass to see this word, so I will see clear vision in center point. Suppose this is my magnifying glass. All right. So I can see from the center clearly. All right, and from the edges I can see the blur portion. So I so this is kind of what, so the image formed by this magnifying glass, image formed by magnifying glass is blurred, blurred from edges and clear vision in clear vision at center. All right, so we can say that our magnifying glass blur the image. So this is the property of what, this property is known as aberration. All right. So if we see a proper diagram, all right, if this is my convex lens, this is principal axis, there is an object which gives a white light. All right. So it divided into its constant colors. This is red color. All right. This is red color, and where it cuts, say this is, all right, this is focal for red, focal length for red color, and there is another color. Say this is blue or violet. All right. So this is violet color, and the focal length for this portion, for this point, is FB. So this region is chromatic aberration. This region is chromatic aberration. All right. So aberration can be specified by its 5 coefficient. All right. So here we can say, we can write, it can be shown that it can be shown that the primary aberration, the primary aberration of of any rotationally symmetric or symmetrical system can be classified, or can be specified specified by 5 coefficient, by 5 coefficients. So what are these 5 coefficients? These are, our first is spherical aberration, spherical aberration. All right. Second one is comma, third one is astigmatism. Astigmatism. Fourth is fade of curvature. Fourth is fade of curvature. And fifth one is distortion. So these are five coefficients that describes any what primary aberration. Alright. So these are called Seidel aberration. Collectively called Seidel aberration. Alright. One more thing. Just note down this. These aberration are present even for light of single wavelength. Single wavelength. They are known as, or they are called, they are also called what? Monochromatic aberration. If you are dealing with what? Single wavelength, then this is what? Monochromatic aberration. Monochromatic aberration. So, in detail, what is chromatic aberration? What is chromatic aberration? That means chromatic aberration means dependency of color. Dependency of color. Alright. So I already discussed chromatic aberration is change in focal length of red into change in focal length of violet color here. So this reason, which reason this? This reason is your chromatic aberration. Alright. If there is no any aberration, this is going to be what? This is white light, this is some convex lens, this is going to be point. For a point object, there must be a point image. There must be a point image. If no aberration. If no aberration. But we have aberration. What kind of aberration? Chromatic aberration. So our beam is spread it out in a region. But if there is no aberration, then the point object will have point image. Alright. So from the chromatic aberration, we know that the change in FR minus FV. If you remember, we know lens maker formula. So lens maker formula says 1 upon focal length is equals to n minus 1 refractive index minus 1 upon r1 minus r2. Alright, r1 is radius of curvature. Alright, for lens 1 and lens 2. Alright, surface 1, surface 2. Alright, good. If we say about red color, for red color, so 1 upon fr is just make it small. For red color FR, this is NR minus 1 refractive index for what? Individual color. For red one, upon C, this is R1 minus R2. Alright, say equation 1. For violet color, 1 upon FV minus NV minus 1 NV minus 1 into 1 upon R1 minus 1 upon R2. Alright, so equation 2. In mid, we can say for a there must be a yellow color, say they are middle color. If you're dealing with your alright, so there will be a middle color or a mean value which is for yellow. Alright, so for a middle one, for a mean value of color, we say we take it as yellow one. Alright, so 1 upon Fy is equals to Ny minus 1 for yellow color, same as 1 upon R1 minus 1 upon R2. Alright, let's say this is equation 3. We know for the chromatic aberration, there is a condition what Fr minus Fv. So for that we need to subtract what 1 upon Fv minus 1 upon Fr. On LCM we will get Fr minus Fv. So say equation 2 minus equation 1. Alright, we are doing subtraction of what equation 2 minus equation 1. So R equals to Nv minus 1 1 upon R1 minus 1 upon R2 minus of Nr minus 1 if we have Nr minus 1 R1 minus 1 upon R2. If we take the LCM, this is Fr minus Fv upon Fr Fv. Right, okay, we had taken what small r, na? So just write it as here small r. Write it down just r, otherwise it will create some confusion. So on taking LCM, we will get Fr minus Fv upon Fr Fv. Good. Which is equals to what? This term is common, so I can take it as 1 upon R minus 1 upon R2 common. So we will get Nv minus 1 minus Nr plus 1. So this is going to be cancelled out 1. Alright. Now if we see, this is Nv minus Nr is equals to 1 upon R1 minus 1 upon R2. Where on the left hand side we have 1 upon minus Fv upon Fr Fv. Alright. So there is a modification. Just make it a step on multiplying and dividing Nv minus 1 on right hand side. So we will see Fr minus Fv upon Fr Fv, which is equals to Nv minus Nr whole upon 1 upon R1 minus 1 upon R2. I said I just need to multiply and divide Ny minus 1. This is going to be cancelled and the value must be 1. So we had multiplied and divided on the right hand side. So I just written with a different color. You will get to know that we had substituted something. Alright. So this is my what? 1 upon Fy from less-maker formula. So we can see Fr minus Fv upon Fr Fv H nv minus nr upon ny minus 1 and multiply by what? 1 upon fy. Already we had already defined for yellow color this equation 3. Alright. If you remember dispersive power, dispersive power. So dispersive power is defined by omega. Omega says a change in violet into a change in effect index upon its mean value. Upon its mean value. So this is for dispersive power. Alright. So this is our dispersive power. So we can know this term is my omega. So I can write it as Fr minus Fv upon Fr Fv is omega multiplied by 1 upon Fy. So Fr Fv multiplied by Fy square. How I written? Just from a geometrical mean. This is what? This is geometrical mean. Alright, so I can write it as what? Fy can be written as into root of Fr Fv. So from here, say this is equation 4. So from equation 4, this is going to be what? Fr minus Fv is Fy square equals to omega on Fy. Alright, so one power cancel out. So we have Fr minus Fv is equals to what? Omega Fy. So this is our chromatic aberration. This is our chromatic aberration. Now, if omega dispersive power is 0, so the right term is 0, then means chromatic aberration is 0. If omega is in that is dispersive power is 0, which means it cannot spread the light. It cannot spread the light. So we can say Fr minus Fv is 0. This is the condition for what? Chromatic aberration. Alright. So on today's lecture we had studied what? Aberration. We had defined what is aberration. Aberration is nothing but the defect in this image, or we find the image blurred. So we define aberration. We had taken an example. Alright, magnifying lens 2. Then after what are the 5 coefficient for primary aberration, and then after derivation for chromatic aberration. So at the last we know Fr minus Fv is going to be omega into Fy, which is chromatic aberration. If the dispersive power is 0, that means omega is 0, then it cannot spread the light, then there will be no aberration, chromatic aberration. Thank you.